S3 is for physics, input, process, and output devices. Within this section, we're looking at all three different types of devices, and there are elements of this section which are more National 4 and others which are more National 5. Throughout this show, I'll highlight which ones are which. Devices. Remember, an electronic system can be split into three parts: input, process, and output. The input part detects or senses or takes in the type of energy. The process part processes that electrical energy, and the output part gives out a useful type of energy. There are only 10 types of people in the world. Only one type can understand binary, and the other type do not.
Logic gates are an example of digital process devices. All logic gates operate from inputs that can be described as on or off, or high or low, or 1 or 0. The three common types of logic gates are NOT gates, AND gates, and OR gates. We can see a decisions module just here. You may have seen these in class before, but if not, I'm going to run through it a little bit. We've got some input devices on the left-hand side. You should have already gone through those. So we've got a switch, a light sensor, a temperature sensor, and another type of switch there. Our outputs on the right-hand side, we can see are a buzzer, a relay, and a lamp. Now, what would happen if we connected the switch, so from point A just here, into the NOT gate? If we turn the switch on, this goes into our NOT gate, and instead of being on, it's not on, so it's going to be off. So if we connect this to the buzzer, say, that buzzer is going to not be working while this switch is on. But if we turn the switch off, then that's going to be not off, because it's gone through our decisions module, our NOT gate. And so not off is equivalent to on, and our buzzer will make a sound that will be on. So basically a NOT gate does whatever the opposite is happening with the input. If the input is off, the output is on. If the input is on, the output is off. Now what about our AND gate? You can see it's got two inputs this time. Let's connect a switch to one of the inputs and a light sensor to the other input. And let's connect our output to our buzzer again, because that's an easy one to think about. For an AND gate to work, both of the inputs need to be on. So our switch needs to be on, and our light sensor needs to be sensing some light, and then our buzzer will turn on. Because it's AND, both of them add up together to make this on at the right-hand side. If our light sensor wasn't sensing any light, if that was off, then our AND gate wouldn't work, this buzzer would be off. This is because both of our inputs need to be on for our output to be on. Let's think about our OR gate. Again, it's got two inputs. So let's connect our push switch at the bottom and our temperature sensor. And let's connect our outputs to the lamp. Let's say our temperature sensor is not sensing any temperatures. So let's say instead of on or off this time, we'll label it 1 or 0, 1 being on, 0 being off. If our temperature sensor is at 0, and our push switch, we are not holding that either, that's at 0, then our lamp is also going to be at 0, so that's going to be at off. However, if we push this switch, so that's going to be a 1 or on, then because it's an OR gate, either the temperature or the push switch needs to be on, and therefore the lamp is going to be on this time. So either the temperature or the switch need to be on for the lamp to be on. So we could switch it the other way around. We could say we're not holding the switch down, but the temperature sensor is sensing a high enough temperature to turn on. So that's a 1. We can put a 1 here, a 0 here, and then our lamp is still going to be on because it just needs to be one or the other. If we were pushing the switch as well as the temperature sensor being on, again, our lamp would be on. By carrying out practical work or research, find out the following for each of the logic gates: the symbol, a statement of how they operate, and a truth table. We've just had a little talk through about how each of the gates work, but if you would like to use a logic gate that you can find, or maybe a simulator online, you can try and find this out. Let's Let's look at them one by one. Here is a NOT gate. We have one input on the left and one output on the right, and our symbol is a triangle with a little circle on the right hand side. The output from a NOT gate is the opposite of the input. Putting this another way, the output is not what goes into it. That's a good way of remembering it, as it's a NOT gate. The output is not what goes into it. This statement can be shown in a truth table. Here is our truth table. Remember the ones and zeros I talked about? If our input is 0, so off, our output is going to be 1, so on. It's always going to be opposites. If our input is 1, our output is going to be 0. We now have an OR gate. This is our symbol here. It has a curved back like an O, and we've got two inputs, input A and input B, and one output. The OR gate will give an output when input A or input B or both inputs are switched on. This statement can be shown in a truth table again. So looking at A and B, if they're both 0, the output has to be 0. However, if A or B is 1, you can see that the output is 1. So that if A is 0 and B is 1, our output's 1. If A is 1, B is 0, then our output's going to be 1. And if A and B are both 1, our output is still going to be 1. And finally, our AND gate. Here's the symbol. It has a straight back like a D, and on the left we have two inputs, input A and input B, and on the right we have an output. The AND gate will only give an output when input A and input B are switched on, and we can see this in a truth table again. You can see from this table, when our inputs are both 0, our output is 0, but when the inputs are a 0 and a 1, or a 1 and a 0, our output is still 0. Both of these inputs need to be 1 for our output to be 1. That's why it's an AND gate, A and B, to give an output. Logic circuits are used in many electronic systems. Here is an example one just here. We've got a magnetic contact switch, an infrared movement sensor, and a master switch, and these are all connected via AND or NOT gates to an alarm box. To design these circuits, you need to think logically. Here are some examples of logical thinking. When you see the word dark, instead think not light. And when you see the word cold, think not hot. So you're thinking opposites here. Here's an example. An electronic device used for a party produces a light-changing pattern when it detects music, but only when it's dark. We need to draw the logic circuit for this electronic device. Remember to think logically. The device needs to detect music and dark. Think logically. Dark is not light, so we want to use a NOT gate here. The logic circuit must use an AND gate and a NOT gate and could look something like this. Here we go, we've got our music sensor and our light sensor. Remember, our light sensor needs to sense not light, that's why we've got our NOT gate in here. And it needs to be sensing both music and not light for it to work properly. So we've got our AND gate here and our NOT gate here. Here's another example. Draw a logic diagram for a seatbelt warning display. When the seatbelt is not in place, so the switch is in the off position, and the ignition switch is in the on position, a warning must be displayed. Remember to think logically for your solution. For the warning to be given, one switch must be not on, and the other switch is on. So the logic circuit again must use an AND gate and a NOT gate and could look something like this. We have our seatbelt sensor up at the top left, and that has to go through a NOT gate because it's the switch being in the off position, and then we've got the ignition sensor. Both of these inputs have to add together. We've got our AND gate to give the warning display output. The next 5 slides have other logic problems to solve, but there's an extra challenge. Can you work out which input devices and output devices should be used with each logic diagram? Good luck! Example 1. Design a logic circuit for a set of hair straighteners. An indicator light comes on when the straighteners have been switched on and they have reached the correct temperature. Remember, you can pause this to have a go at the examples before you have a look at the solution. So, if we want the hair straighteners to show an indicator light if they're switched on and the temperature is high enough, we need 2 inputs, don't we? One of them is just a simple switch, That's our first input. And the second is going to be a temperature sensor. Now we want the temperature sensor to sense a high temperature, so we don't need to say not at all. We don't need to put a not gate in there. We just need when the switch and the temperature sensor are both on. So it's an AND gate. We need both of them to be working to give us an output. So this is our AND gate, and our output is going to be an indicator light. So that's our full diagram there. We've got a switch and a temperature sensor. They both have to be working, so we've got an AND gate, and then we've got an indicator light. Example 2. Design a logic circuit for a doorbell. The doorbell has only to work when it's switched on at night time. So let's think about what needs to happen for a doorbell to turn on. Well, someone needs to press the button, don't they? So we could say a switch or a push switch or a button there. And also we need a light sensor. Remembering back to our logical thinking, if it's night time, that's dark. And how do we say dark? We say not light. So next to our light sensor, we need a NOT gate. Remembering what your NOT gate looks like, we have a triangle with a little circle on the front there. And we can join up our push switch. And these both have to be used. So we're using an AND gate there to give our output, because the doorbell has to work both when it's pressed, so when the switch is on, and when it's night time. So that's why the AND gate is being used. And then we can just put a bell on this side, doorbell. So we have the push switch on, we have a light sensor, but not light. So it's dark, it's night time, and both of these have to be happening for the doorbell to turn on. Example 3. Design a logic circuit for a baby alarm. The alarm has to give an output when it's switched on and the baby makes any kind of sound. So again, just like with our last two, we need a switch, don't we? We need to turn the alarm on before it's going to work. And we also need a noise sensor or sound sensor. So we have to have it switched on, we have to be detecting noise, so we don't need any NOT gates in here, but we do need an AND gate. Both of these things have to add together there, an AND gate. And then our alarm has to turn on, so we can just say alarm on the right hand side. So that's our final diagram there. We've got a switch and a noise sensor, both detecting an input, and our alarm is our output. Example 4. Design a logic circuit for an interior light in a car. The light should come on when the passenger door or the driver door or both are opened. So let's have a think about how cars work. We want some sort of sensor to detect when the car door is open or closed. So let's say car door sensor. If the car door is open, that's like saying the switch is open. But we need the circuit to detect when the car door is closed. And thinking back to our logic, closed equals not open. So we need a NOT gate in here. We actually need two car door sensors because it's when the passenger door or the driver door is open. So we can say the car door sensor for the passenger up here. And another one underneath, a car door sensor for the driver. And just like before, we're going to need a NOT gate here because it's not open, it's closed. The light should come on when the passenger door or the driver door, oh, that's a rubbish highlighter, isn't it? Or the driver door or both are opened. So it's not an AND gate we're using this time, it's going to be an OR gate. Remembering what your OR gate looks like, we've got curved back to it, and then we've got our output, which is an indicator light. Oh, not indicator light, interior light even. Those little lights that no one ever likes being on when it's dark. And that's our final diagram there. Example 5, this is our last one. Design a logic circuit for turning on a heating fan at night when the temperature is too cold. So thinking about this, we want to turn on our heating fan, so we need a switch again. A lot of these circuits have switches in them. And we're thinking about the cold. Cold is equal to not hot. And this is talking about temperature, so we can say a temperature sensor. Because cold is not hot, we need our NOT gate in there. But the switch is just going to stay on, so we don't want opposites there. Joining these together, they both want to be turned on to turn the heating fan on, so we want our AND gate. And then we can put on the right hand side heating fan. So both the switch has to be turned on and the temperature sensor has to be sensing not hot, so it has to be sensing cold. These are both added together, then we've got our heating fan. Process devices, transistors. There are many different types of transistor, and in this course we will study 2 different types. Transistor. We have an NPN bipolar transistor, which looks like this, with the base on the left, collector on the top right, and emitter on the bottom right. We also have a MOSFET. We have a gate on the left, a drain up at the top right, and a source down at the bottom right. Transistors act like an electronic switch. They switch on when they receive a high enough voltage, and a typical NPN bipolar transistor will switch on at around 0.6 volts. A typical MOSFET will switch on at around 2 volts. Transistors are often used along with potential dividers in electronic control devices. Transistor questions usually need you to identify the components in the circuit and explain how the circuit operates. You must remember LURD, so light up, resistance down, TURD, so temperature up, resistance down, and potential divider theory. And that low resistance needs a low voltage, and that a high resistance needs a high voltage. Example 1. Explain how the following transistor circuit operates. Here we've got our circuit. We can see different components in there. We've got our variable resistor, if you can see my little pen just here. Here we go, our variable resistor. We have a thermistor just here. We have a MOSFET, we have a relay, and we have our heating circuits over here. First, we identify all the components, which we've just done, and this will let you work out what quantity changes to let the circuit operate. This particular circuit will react to changes in heat/temperature as component X is a thermistor. You now need to understand the terms LURD and TURD. For this circuit, TURD is used, temperature up, resistance down. Now ask yourself what will happen to the voltage when the resistance changes. Remember, voltage will always go down when resistance goes down, and vice versa. Next, you have to work out how to turn on the transistor. This will always happen when the voltage across the transistor is increased to the switching voltage. So, for the above circuit, we need the resistance across the thermistor to increase. This will create big enough voltage across the transistor. For the resistance to increase, the temperature must go down. Always finish with the statement about what happens when the transistor is switched on. In this case, current flows to the relay and the heating circuit is switched on. Example 2. An electronic circuit that's used to control an automatic blind is shown below. Name the type of transistor used in the circuit and explain how the circuit operates to close the blind. Here's our circuit. You can see that there is an LDR, so a light-dependent resistor, a variable resistor, a type of transistor there, and a motor. So our first part of the question was to name the type of transistor. That is a MOSFET. And the second part of the question was to explain how the circuit works to operate the blind. First of all, we need to remember LIRD. When the light level increases, the resistance of the LDR will decrease. Less of the supply voltage will then be needed across the LDR. That means more of the supply voltage will be needed across the variable resistor because it has to keep a balance. Our supply voltage, this 12 volts here, is staying the same. So if less voltage is used here, more voltage will be used here. This means that there'll also be more voltage across the MOSFET just here. When the voltage across the MOSFET increases to the switching voltage, so remember that's approximately 2 volts, it will switch on. The current will flow to the motor and the motor will then be turned on. Let's look at some past paper questions. An office has an automatic window blind that closes when the light level outside gets too high. The electronic circuit that operates the motor to close the blind is shown. This is a really similar circuit that we just looked at before. And the question is, the MOSFET switches on when the voltage across the variable resistor R reaches 2.4 volts. Part 1. Explain how the circuit works to close the blind. And Part 2. What is the purpose of the variable resistor R? Let's have a go at Part 1 first. So we need to explain how the circuit works to close the blind. Looking at the question itself, we can say the blind closes when the light level outside gets too high. So this is what we can start with. The light level increases. And remembering back to LIRD, light up, resistance down, we can say the light level increases, so the resistance decreases, but we need to be specific. We need to say that's on the LDR. So if the resistance of the LDR decreases, the voltage of the LDR is also going to decrease. A low resistance requires a low voltage. Remember, you need to be specific. You don't just say the voltage decreases, you say the voltage across the LDR decreases. So if the voltage decreases across your LDR, remembering that our supply voltage is staying the same, if the voltage here is decreasing, the voltage here must increase. So our next sentence is the voltage across the variable resistor increases. If the voltage across the variable resistor increases, that means the voltage across the MOSFET must increase. And for our last little sentence, we can say because the voltage is increasing across here, the MOSFET turns on. It allows the current to flow. That's the current flowing through the motor, which turns the motor on. This is quite a lot of writing, but it is worth 3 marks, and all of this would get you your 3 marks. Let's look at part 2. What is the purpose of the variable resistor R? So why do we have this variable resistor here? This is actually to control at what light level the blind starts to close. So this says either at a really, really bright light or a kind of medium dim light. So whatever you turn your variable resistor to is going to determine what light level makes the blind close. Part B. The graph shows how the resistance of the LDR varies with light level. You need to determine the resistance of the LDR when the light level is 70 units. So we've been told the light level is 70 units. Let's find that on the graph. If you've been given a graph, you're definitely going to have to use that. So we've got 50 just here. We can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions between 0 and 50. So your 70 units is going to have to be just here, because we could go 50, 60, 70, 80, 90, 100. Every 10 units is 2 boxes. Let's follow that up to our line that's on the graph. And then we want to follow it across to the resistance. So they've given us quite a nice graph here. It's an exact line that we're following along. Excuse my wobbliness of the line. We're coming out about just here. That's going to be directly between 2,000 and 4,000, which is 3,000. So it's only worth 1 mark just here. So you can just state an answer. Your resistance is 3,000. Don't forget about your units, 3,000 ohms. Part 2. The variable resistor R is set at a resistance of 600 ohms. Calculate the voltage across R when the light level is 70 units. First of all, let's bring back our circuit diagram, and we can add on some numbers to this. So we can see we've already got 12 volts on there. That's our supply voltage. We've just been told the variable resistor R is set to a resistance of 600 ohms. So there's 600 ohms just here. And calculate the voltage across R when the light level is 70 units. That was in our previous question. We, from the graph, figured out that when the light level is 70 units, the resistance across our LDR is 3,000 ohms. So that's this other resistance up here. We want to work out the voltage across R. Making a nice little list, we have our resistance across R, that's 600 ohms. We have our resistance across the LDR, 3,000 ohms. And we have our supply voltage, which is 12 volts. When we look at our equation sheet, to figure out our voltage, there's 2 possible equations we could be using. We can see that there's V2 equals R2 over R1 plus R2 multiplied by Vs, or V1 over V2 equals R1 over R2. Sometimes it can be difficult to spot which one we should be using, but in this case, we can see that we do not have our second voltage. We want to be working out this VR. This is what we want, but we don't have V of the LDR. We don't know what that is. So we can't use this second equation just here. We have to use the first one. So let's say, giving labels to 1 and 2, if we say that our resistor is 1 and our LDR is 2, just so we can keep our numbers consistent, V2 equals R2 over R1 plus R2, all in brackets, multiplied by Vs. Oh, that's a 2. And let's start plugging our numbers in. R2 is 600, because that's our resistance of the variable resistor. R1 plus R2 is 3,000 plus 600. You multiply all of that by 12. Popping that into your calculator gets you to 2 volts. There we go. So the voltage across R when the light level is 70 units is 2 volts. Part 3. State whether or not the blinds will close when the light level is 70 units. You must justify your answer. Let's look back to the beginning of the question. We've got some quite important numbers. We can see next to where it says Part A, the MOSFET switches on when the voltage across the variable resistor R reaches 2.4 volts. We just worked out that at 70 units, as it's specified in the question, the voltage of our resistor R is 2 volts. We just looked at that. So do we think the blind is going to close or not? No, the blind will not close. This is because the voltage of the resistor is at 2 volts, and 2 volts is less than the 2.4 volts it needs to reach to activate the MOSFET and let the motor turn on. So 2 volts is too low, it's less than the 2.4 it needs, so the blind will not close. Let's look at another question. A student investigates the electrical properties of 3 different components, a lamp, an LED, and a fixed resistor. Current voltage graphs produced from the student's results are shown. Explain which graph, X, Y, or Z, is obtained from the student's results for the LED. Let's think about what LED stands for. An LED is a light-emitting diode. And what do we know about diodes? Diodes only allow the electricity to pass in one direction. So the current can only flow through them one way. If it tries to flow through back the other way, it does not work. So the current can only flow in one direction. Looking at our graphs, we can see that graph Y and graph Z both show values on the negative and the positive side of the current axis. However, graph X shows a 0 value along here. You can see this, there's no part of the graph below this line. So graph X is our LED graph because the current can only flow in one direction. We can see the current is flowing up here. This current is above the 0 value, and it's not flowing below 0. It's at this 0 line just here. So we've already given the justification, current can only flow in one direction. We just need to give our answer. It is graph X. Part B. One of the components is operated at 4 volts with a current of 0.5 amps for 60 seconds. Calculate the energy transferred to the component during this time. With questions like this, we always want to make a little list of what we know and what we want to find out. So initially, we have got our voltage just there. I'll highlight these first. We've got our voltage, we've got our current, we've got a time just there, and we want to calculate energy. So V is 4 volts, I is 0.5 amps, T is 60 seconds, and we've got a question mark next to our E. Now looking at your data sheet, there is no equation that involves all 4 of these to work out your energy. We're going to have to use 2 equations. Looking at E and T, we can relate these with the equation from your equation sheet, P equals E over T. So we've got power just here. Let's look for an equation that involves power and also voltage and current, and we come up with P equals IV. So first of all, using P equals IV, we work out P to equal 0.5 times by 4, so our power is 2 watts. Then we need to use P equals E over T, so we've got 2 equals E over 60, E equals 2 times 60, so our energy is 120 joules. That's why this is worth 4 marks and not 3, because you need to use 2 equations. Part 2. Calculate the charge which passes through this component during this time. So we want to work out charge this time. Charge is a Q. And looking at our equation sheet, we can see that the equation we want to be using is Q equals IT. Because we have I, that's 0.5 amps, and we have T, that's a time of 60 seconds. So Q equals 0.5 times 60, so our charge is equal to 30 coulombs. Let's try another question. The temperature of the water in the washing machine is monitored by a circuit containing a thermistor. As the temperature of the water increases, the resistance of the thermistor decreases. The heating element is switched off when the temperature of the water reaches 40 degrees C. Explain how the circuit operates to switch off the heating element. They've already given us a little bit of information here, so we can start off by saying, as the temperature of the water increases, the resistance of the thermistor decreases. So our temperature goes up, and then the resistance of our thermistor decreases. Now, this is what I already said in the first sentence. It's always useful to summarize it for yourself. If the resistance of the thermistor decreases, we need to mention the voltage next. If the resistance goes down, the voltage also goes down. So, therefore, the voltage, and you have to be specific here, the voltage across the thermistor decreases as well. If the voltage across the thermistor decreases, that means the voltage is also going to decrease across your MOSFET. Therefore, if the voltage is decreased, current cannot flow. And the relay turns off. Therefore, the switch is open and the heating element is turned off. And that's all of your answer just there.